In this video, we are going to explore Pandas, one of the most popular Python libraries for data analysis. Pandas is built on top of NumPy and provides powerful tools for data manipulation and analysis. It's often used for handling large datasets, and it makes working with structured data much easier. Pandas gets its name from the term panel data, so it's primarily used for working with structured data such as tabular data, time series, and matrix data. Pandas' basic building block is the Pandas series. A series can hold an array of information organized by an index, similar to a single column in a spreadsheet. At first glance, this seems what NumPy does, right? Well, Pandas builds upon NumPy, so it is similar. But unlike a NumPy array, a Pandas series can use a named index as well as a numerical index. Let's begin by importing the necessary libraries for this notebook. First, NumPy SNP, and then we import Pandas SPD. Up until now, we've organized data using Python lists, arrays, and dictionaries. For example, here's how we would store population data for 3 cities in a list. In this case, the first list holds the city names, and the second list holds the population information for those cities. In the last lecture, we also got to know NumPy arrays, so we could also store those lists in NumPy arrays if we wanted to. Currently, the cities and their corresponding population information are stored in separate variables, which is not very convenient. Sure, we could create a nested list or a two-dimensional array to store the city and its respective population together, but there are better ways to do this. We learned about dictionaries, which can store the city names as keys and the population counts as values. This already looks more efficient, but Pandas series can do it even better. The great thing about Pandas is that we can input data in almost any format we have discussed, and Pandas will create a series from it. Let's start by taking just the list of population numbers and turning it into a Pandas series. We can use the pd.series function and pass the list variable as data. The data parameter is provided by Pandas, as you can see in the documentation. Since this is the first parameter, we don't really need to specify it explicitly. We could also just pass our data without saying data equals. Pandas creates a series from our list and automatically assigns a numerical index to the rows. As I mentioned earlier, this index doesn't have to be numerical. It can also be customized. Let's create a new series, this time specifying that the index should be the city names. By passing the labels list as the index, we can associate each population number with its corresponding city. This gives us a Pandas series where each value is indexed by a label rather than a number. And remember when I said Pandas doesn't care whether we provide a list, an array, or a dictionary? This means I could also use the arrays instead of the lists and get the same result. Or I could simply pass a dictionary into the series and wouldn't even have to worry about what is the data and what is the index. Pandas figures that out by itself and returns a perfectly structured representation of our data. If we want to receive specific information back from this Pandas series, we can use label-based indexing. For example, to get the population of the city Bochum, we simply refer to this series by the label Bochum. A Pandas series works well for one-dimensional data that might need a specific index. However, as soon as our data becomes two-dimensional, so more than just a single column, we need Pandas DataFrames. I would like to set up a data frame with some dummy data. For that, I will use some random numbers from np.random.randn with a shape of 5 rows and 4 columns. This will be our two-dimensional input data. Now I would like to have custom indices, which I will provide as a list. Since I have 5 rows of data, I need 5 indices, for which I will use the letters A to E. I also need 4 headers for the columns, for which I will use the letters W to Z. If I am unsure how to put all of this together, I can refer to the documentation. There I see that I can provide the input data with a data argument, the A to E indices with the index argument, and the column names with the columns argument. So I follow the documentation exactly, setting up a variable called df, short for DataFrame, calling pd.DataFrame, and passing all the variables. I think we can agree that this looks very well organized. Now let's see how we can retrieve specific elements from this data frame. Selecting a column in a data frame works the same way as selecting by index in a series. We just take the data frame variable and provide the name of the column we want within square brackets. That's how we retrieve the specific column. Now let me show you something. Testing this specific column's data type, we can see that a data frame consists of several series. Each column is a series, but putting them together results in a data frame. We just saw how to select a single column from our data frame. Now let's figure out how to select multiple columns. I will do this in 2 steps. First, I set up a list with the column names I would like to retrieve, such as column W and column Z. Then I pass this list in square brackets behind my data frame. Whenever we want to select multiple columns, we need to provide them in a list, which typically has square brackets. The selection itself is also done with square brackets. Of course, we can shorten this selection into a single line of code by directly providing the list of columns within the square brackets of the selection. Now we know how to select columns from a dataset. But what about the rows? If you try to select rows the same way as columns, such as df of A, you will get an error. The best way to select rows is by using the lock method. By calling lock on your data frame, you can specify named indices. This way, we receive all elements of the specified row. Notice that the column names switch to become the indices in this case. That's because our selection returned a single row of data, which is one-dimensional. As you know, Pandas manages one-dimensional data with a series, so this selection returned a series. What if we want to select more than just a single row of data? We use the lock method again, and just like when selecting multiple columns, we provide a list of the row indices. So I will pass a list with the index names A and B. This time the selection returns a data frame because I still have two-dimensional data. But what if I don't know the named indices and only care about the row's position in the data frame? Even though we are using named indices instead of the default numerical indices, Pandas still tracks the numerical indices, allowing us to make position-based selections using the ilock method. For example, df.ilock of 0 will return the first row of data. The selection and slicing syntax for ilock is the same as a NumPy arrays, so we can also select the first 2 rows with colon 2. Or select rows from index 2 up to, but not including, index 4. As a last example for slicing, I would like to show you that slicing is also possible with the named indices using the lock method. The first list is for the named indices, where I will select A and B. And the second list is for the column names, where I will select Y and Z, for example. Although selecting and slicing elements in a pandas data frame is a big and important topic, we need to discuss some other topics as well. Just like with an Excel spreadsheet, we can also perform calculations on the columns and write the results into a new column. Setting up a new column is super easy. You just take the data frame and assign a new column name that doesn't exist yet. To fill it with content, we can write a constant number or a string, or we can perform calculations between existing columns, like adding column X to column Z. Columns can be removed using .drop. You provide the column name and specify the axis along which to find the name. For columns, it's axis 1. If we want to remove it from the current data frame that is associated with the variable df and not save it under a new variable name, we also need to make it an in-place operation. Removing rows by their index name works the same way, except that we operate along axis 0. Rows are axis 0 and columns are axis 1.